Um, so, as those of you who were in my talk yesterday will know, the reason why I'm here is because I've recently had this book published, Concurrency Models in 7 weeks. And what I'll be talking about today is broader than the topic of the talk yesterday. So yesterday I was talking about specifically concurrency and closure. What I'm going to talk about today is concurrency in a broader sense, and in particular I'm going to look at some of the problems with traditional threads and locks based concurrency, and then give you a flavour of some of the approaches that are available to help you avoid those problems. Now, as I said yesterday, my hobby is playing with race cars. And playing with race cars is a particularly good way of throwing money away. It's also a very good, I think, example of concurrency and some of the problems with concurrency, because driving a car around a circuit isn't a particularly dangerous thing to do when you're by yourself, but of course you're never by yourself. And when you've got lots of cars sharing a race circuit, you tend to get contention. Now, I showed you an interesting photo of contention yesterday. I'm going to show you a different set of photos. So this happened not to me, actually. Thankfully, this was a guy with whom I touched wheels a few years ago, and I think this is a particularly lovely. I mean, that photo in particular, I think, is great. Oh yeah, no, they were fine. This photo actually won best motorsport photo of the year 4 years ago, which was quite good. So there you go. It's a series of photos. So anyway, this is what we don't want to happen in our parallel code. So, what makes multi-threaded code hard to write? Well, there's lots of things that make multi-threaded code hard to write, and you know what most of these things are. There's deadlock, there's live lock, there's lock contention, there's scalability, there's priority inversion, and it goes on. I'm not going to talk about any of these things, because these are the things that people talk about on a regular basis. If you read books about concurrency, you'll see lots of mentions of all of these things. And actually, I don't think that these things are the difficult things about writing code. I mean, I'm not suggesting that they're easy, but these aren't the really difficult things. The really difficult thing is memory and the memory model. So when I say memory model, what do I mean? Well, for that, I'm going to have to give you a little bit of context. So I'm going to show you a very hackneyed graph. You've seen this graph hundreds of times. This is Moore's law, yes? So we've got transistor counts increasing exponentially. The scale on the vertical scale on this graph is log scale. So our transistor counts are increasing exponentially, and right now, at least, there's no sign of this slowing down. But, as everybody knows, single core performance is tailing off. And this gap here, this is what we keep talking about as the multi-core crisis. Now, this is an interesting thing to talk about, but actually, I don't think this is the interesting bit of this graph. The interesting bit of this graph is this bit. Why is it that going from 10,000 transistors on a chip up to 10 million transistors on a chip gives us a performance increase? I mean, if you think about it, it's not obvious. If I just throw lots of transistors at a problem, does that make my chip faster? So why is it that from 1970 through to about 2005, so for 35 years, why is it that the performance of our chips was scaling in proportion to the number of the number of transistors that were on those chips? Well, there are a few reasons. One is increasing clock speed. So as our transistors get smaller, they get faster. So we've gone from the kind of CPUs that were around when I was a kid that were running as a few megahertz up to the kind of transistors we've got today that are running in the gigahertz. So that's part of it. But that doesn't tell you why lots of transistors make things faster. That just tells you why small transistors make things faster. So what else is going on? Well, part of it is bit level parallelism. Why is it that a 32-bit CPU is faster than an 8-bit CPU? The answer is parallelism. If you want to add two 32-bit numbers together on a 32-bit CPU, you do it as one instruction. If you wanted to do the same thing on an 8-bit CPU, you'd have to do it as a sequence of 8-bit instructions. So a 32-bit CPU is faster than an 8-bit CPU because it's more parallel than an 8-bit CPU. But even that doesn't explain why going from a few tens of thousands of transistors to 10 million transistors makes your CPU faster. Because you only need to increase the number of transistors on your CPU by a factor of 4 to go from an 8-bit CPU to a 32-bit CPU. So why are all these transistors helping us? Well, the answer is instruction-level parallelism. You think, or we think, of our CPUs as being sequential. We run instruction A, then we run instruction B, then we run instruction C. And they go to great lengths to make it look like that's what's going on. But in fact, our CPUs are doing a massive amount of parallelism under our feet. They're doing speculative execution, they're doing branch prediction, they're doing pipelining, and a whole bunch of other things which are all there in order to make these CPUs go faster. Now, most of the time, we're completely unaware of the fact that all of this is going on under our feet. And in fact, if you've only got a single core, you can be almost entirely, unless you're writing a device driver or something really low level like that, you can be entirely unaware that this is going on under your feet. But these days, we're not running on a single core. These days, we're running on multiple cores. And when you're running on multiple cores, all of a sudden, this becomes very, very relevant. And the place in which it becomes relevant is when you start thinking about the memory model. So I'm going to show you what I mean by that, and I'm going to show you what I mean by actually showing you some code. So here we go, I'm going to start with this. So here I have, oops, no I don't. Here I have an incredibly simple little class. Hello. I don't know. Can you guys hear me? Is this not? No, this is, there doesn't seem to be anybody at the back. So, okay, I'll try speaking up and shout at me if you can't hear. So this class is creating two threads. It's creating thread 1, which is called T1. It's creating thread 2, which is called T2. Both of them are looking at these two static variables. We've got one called answer ready, which is a Boolean, and we've got one called answer, which is an int. What T1 is doing is it's writing the number 42 to our variable called answer, and it's writing true to answer ready. And thread T2 is looking at answer ready, and if answer ready is true, it's printing out the meaning of life, and if answer ready is false, it says it doesn't know what the meaning of life is. This is very, very simple code. It should be extremely easy for every single person in this room to predict what this might do, yeah? So what might this do? What are the answers we might get out of this piece of code? Anybody? Come on, we've got how many experienced developers in this room? We must have somebody here who's confident to predict what this code will do, yes? Well, there are two obvious answers, yes? It might print the meaning of life is 42. That's one possibility, yeah? Everybody agree with that? No? We've got shaking. Well, I can tell you, it might do that. That is one of the possible answers. It might print out, I don't know the answer, yeah? So those are two possible answers that we could get from this. But actually, there's one other thing that it can do. It might print out, the meaning of life is 0. Now, how the hell can it do that? I mean, this is weird, yeah? We're writing the answer 42, and then we're writing true to answer ready into memory. So the only way that this could possibly print out the meaning of life is 0 is if something is flipping these two lines of code. Yeah? Those two lines of code have to be switched in order for this to be able to print out the meaning of life is 0. But it can do that. And the reason why it can do that is genuinely because something might be flipping the order of those two lines of code. And in fact, it's not just one something that might flip those two lines of code. Your compiler might switch them around. The JVM might switch them around. The hardware that you're running on might switch them around. It gets weirder. If I change this code, So that instead of saying this, it says, while not answer ready, do nothing, and then print out the answer. Now what can happen? Nobody prepared to give it a go? Well, it's almost the same. It could print out the meaning of life is 42. It could print out the meaning of life is 0. But actually there's something else it could do. It might never terminate. Sorry? Yes, it'll wait forever, potentially. It might never see that answer ready becomes true. So again, how can this happen? You know, we've got a piece of code up there that's clearly writing true to the variable, yeah? And the reason why it might not ever terminate is because, again, the compiler, the JVM, the hardware that you're running on, is quite capable of looking at this thread, the first thread T1, and saying, nothing's using true. Nothing's ever using the value of that, so I'll just not bother writing it to RAM. And that's a perfectly reasonable thing for it to do. Now, what I hope you're now asking yourself is, how do we make any guarantees about any of our code ever if all of this weird shit can happen? And the answer is, we can constrain when values are written to memory. And the way that we do that is through synchronization. So this is where things like mutexes, atomic variables, volatile variables and so on come in. The reason why this code is so bizarre, or might behave so bizarrely, is because there's no synchronization in it. If I was to make these methods synchronized, now all of a sudden we have some guarantees about what will happen. But the problem is, when you write Java code, there's nothing that the compiler will do to tell you that your code is properly synchronized. If you accidentally miss a synchronized off one of your methods, nothing will tell you that you've done that. And as soon as you do that, you make one mistake anywhere at all in your code, this kind of bizarreness can bite you. And what makes it even worse is that I've told you that that's what might happen. You're not likely to actually see it. I mean, if you actually run this code, you'll probably see it do sensible things. And it will do sensible things, probably 999 times out of 1,000 times you run this code. But one time out of 1,000, you'll see the bizarre thing. Now, how are you supposed to debug that? How are you supposed to understand that? And that's the problem that we've got when we're writing multi-threaded code. It's not just this. Yes? With this code, no. The problem is, this code's too simple. And in this code, probably the JIT, the compiler, all the rest of it, they won't bother optimizing it. It's only when you've got complicated code that this weird stuff happens, but that makes it worse. Because in the complicated code, it's even harder to work out what's going on. You just, every once in a while, you get some weird thing not get written to memory, and you've got no idea why. So actually, that's the fact that this code works is a bad thing, because it's incredibly easy to sucker yourself into thinking that you've got good code that works, until all of a sudden, at 3 o'clock in the morning, your server crashes, and you've no idea why your server has just crashed. So it's not as simple as this. There are other things that can go wrong, and I want to show you a few other examples of some of these weird things. So I'm going to show you another piece of code that has a problem in it. So here we have another incredibly simple piece of code. All it's got is it's got a date format member, and we're going to use that in order to parse a string. Now, our date format member is private, so nothing outside this class can access it, and it's static. We only write to it at the time that the class is created. So there can't be any threading issues here, yeah? Nothing's changing the value. I can call this class for as many different threads as I like. I can't possibly have any threading problems. Everybody agree? No? Do you know why I got threading problems in here? Date format is not thread safe. How do I know date format is not thread safe? I'm looking at this code. So as you know, not that, well, okay, the Java doc now finally tells you this. But I'll tell you how most people find this. Most people find this by running this code and having it work just fine until, at 3 o'clock in the morning, their server crashes. And then they spend hours or days or weeks debugging this. And then eventually they find that one line in the Java doc that says date format is not thread safe. And this isn't unique. Date format happens to be one example of this. But there are many, many classes within the JVM and within the code that we all write which aren't thread safe. Because how are you supposed to tell? There are other examples, and I'm going to show you another one. Where are we? So here we have, no, that's not what I meant. I meant this. Here we have, and I'm not going to go through this code in detail, but here we have a class which you give it a URL and it will download from the URL. The interesting bit is this bit here. So as it's downloading from the URL, it's going to call a listener. And the listener is just defined like this. So it's a little interface that just says, I want to know how far through the download I've got. Now, oops. What is it about this piece of code that's going to cause us problems in a multi-threaded environment? Anybody? No? So you're right, that is one of the problems with this code. Actually, that isn't the problem which I'm interested in this particular instance, but you're quite right. If somebody changes the listeners while we're calling this, that is a problem. But actually there's something much, much worse wrong with this. And the thing that's wrong with this, the really bad thing that's wrong with this, is we've got our nice synchronized class here, which is taking a lock before it calls the listener. It has no idea what the listener's going to do. One of the things the listener might do is claim another lock. There's no way to stop it from claiming another lock. Now, what if it claims another lock that the thread, or some other thread, has already got? Now, at this point, potentially, we've got deadlock, because we've no idea, we've no control over what that other lock might be. And one of the best ways of avoiding deadlock is to have a global ordering of locks in your code. Well, we can't enforce that here, because we're calling a function that we have no knowledge of. Now, there are ways in which we might be able to restructure this to avoid that problem. But again, there's nothing in the compiler, there's nothing in the language runtime, there's nothing anywhere that's going to tell us that we've hit this problem. And this kind of thing happens all the way through multi-threaded programming. There are pitfalls which those of us who've got the scars in our back know about, and the vast majority of us who haven't yet got the scars in our back are blissfully unaware of. But even though I've got lots of scars in my back, I have no way of looking at a piece of code and knowing that that piece of code is correct. And in particular, I've got even less idea of how I can write a piece of code where, even if it's correct today, it will remain correct in a year's time after all the other people in my team have come in and they've modified the code and they've refactored it and whatever. So what are we supposed to do as programmers in order to avoid these kinds of problems? And the simple answer is there's nothing that we can do as programmers to avoid these kinds of problems. These are just intrinsic to writing multi-threaded code. If you're writing thread and lock based code on the JVM, in C++, in any other language that supports threads and locks, these problems are unavoidable. The only way that you can avoid them is by sitting down and reading your code really, really carefully. And then when you've finished reading your code really, really carefully, sitting down and reading your code really, really carefully some more. And then every time anybody makes any change to your code, sitting down and reading your code really, really carefully. And this is not a good way of writing source code, and it's definitely not a good way of guaranteeing that what you've got is a working piece of software. So, let me go back to our presentation. I'm going to show you one other example, which you guys who were in my presentation yesterday will recognise. This is another example of code that, on the face of things, is well written, but actually has a concurrency bug. We've got a class here which has a private member variable. We've got two synchronized methods. We only ever access our private variable when it's synchronized. But again, this isn't thread safe. And the reason why it isn't thread safe is because when we return an iterator over that, it's outside the lock. So anybody who's using this iterator after the fact will end up with concurrency issues. And again, nothing in the runtime is going to warn you about this. The only way that we can spot this is to look at our code really carefully. So, what's the elephant in the room? What's the thing that this is telling us? Testing. One of the things that has changed, the most important thing to my mind that's changed in software development over the last 10, 15 years, is that we as an industry have worked out how important testing is. Refactoring absolutely depends upon testing. Agile development absolutely depends upon testing. The reason why we can move from the old-fashioned waterfall model, where we release every 6 months, every year, or whatever it is, with a big integration test and all the rest of it every 6 or 12 months. The reason why we can move from that to the situation where we release every 2 weeks, every week, maybe even every time we commit source control, the reason why we can do that is because we've got regression tests. Well, regression tests are great, but how do you write a regression test for concurrency bugs? And the answer is, you can't write a regression test for concurrency bugs. There is no way to create a test that will find the problems that I've just shown you. Sorry, I don't know, I've forgotten your name, but the gentleman who asked the question about have I made this code go wrong, that illustrates why you can't write a test for this. Because actually, most of the time, it won't go wrong. It'll only go wrong on the 1000th time that you happen to run your code. And if that's the case, then the only way you're going to find out is when your server crashes at 3 o'clock in the morning. And that isn't a world that I want to live in. So what's the bottom line? The bottom line is multi-threaded programming is really hard. In fact, it's not just really hard, it's really, really hard. And there is no solution to this with threads and locks. Now it gets better. There are solutions, they just don't involve using threads and locks. So what's the problem? At heart, the problem is shared mutable data. So anytime you've got a piece of data that's shared between 2 threads and that both of them can change, now you have a problem. Actually, not even as much as both of them can change it. One of them can change it, you have a problem. And there are various different ways in which you can choose to tackle this. So functional programming addresses this problem by getting rid of mutability. You can still share data between threads, but because in functional programs all data is immutable, you don't have shared mutable data because you don't have mutable data. Now, this is broadly what I was speaking about tomorrow, and I'm not going to cover this any further here, but that's one very sensible way of addressing these issues. An alternative are message passing approaches, like actors and communicating sequential processes. And what I want to do in this talk, in the remainder of this talk, is just show you quickly some of the ways in which message passing helps with solving some of these problems. But just for completeness, the other approach is, broadly speaking, what I covered yesterday, which is the closure approach of still retaining shared mutable data, but doing it in a mostly functional environment where the persistence that's provided by closures data structures allow you to retain shared mutable data, but without hitting some of these problems. But that was the topic that I spoke about yesterday, and I'm not going to spend any more time on it now. So, like I said, I want to spend a little bit of time talking about message passing, and in particular I'm going to talk about actors. Now, how many people here, just so I get a rough idea, how many people here have heard of actors? Yeah? How many people here have used actors? Okay, so we have a few people who have, but the majority have heard of, but not actually used. So what I hope to be able to do in the remainder of this talk is show you a quick example of an actor program and convince you that by moving from the traditional threads and locks model to an actor-based model, you gain a bunch of things. You gain reliability and confidence that your code works, but actually you gain a bunch of other things. You're going to gain the ability to run your code on distributed hardware, and you're going to gain the ability to recover when you have a failure. So we're not getting just an improvement in the quality of our code, we're getting a step change in what it is our code can actually do. So, what is an actor? Well, personally, I think the best way to think of an actor is it's actually object-oriented. We've been programming object-oriented code for years, but really, object-oriented programming is about messaging. Alan Kay, who's the guy who invented object-oriented programming, has famously said that he doesn't think he should have called it object-oriented programming because that puts the emphasis on the wrong thing. It puts the emphasis on the objects. Actually, the interesting bit are the messages. An actor is like an object, except it genuinely is something that receives messages. Unlike most object-oriented programs, where when we say we're sending a message to an object, what we're really doing is calling a method. In an actor, we're sending a genuine message. So let's see an example of that. So I'm going to show you one really simple actor. Now this particular actor is a counter. So it's not dissimilar to some of the code we've seen before. We've got a mutable variable called count. This is written in Scala, which I don't know how many people in this room are familiar with Scala, but hopefully the syntax is relatively simple to work out. So this is just declaring an integer variable called count, and then this is declaring a method called receive, which has two cases, increment by and print count. Now this is pattern matching. I'm not going to talk about pattern matching, but I hope it's relatively clear what this actually means. Yes, so this is an actor that can receive two different messages. One message is called increment by, and one message is called print count. So let's see how we actually use this. So I'm just going to create a console which I can type things into, and I need to do one little piece of housekeeping, which is to create an instance of this actor. So I'm going to say val counter equals system dot actor of So what that's done is it's created an instance of my actor, and now I can send messages to it. So I can say counter shriek, and shriek is the send operator. So counter send increment by, let's say, 2. And then I can say and it's worked that out. And if I send it another value and print it, I've now got a different answer. Now the question is, why is this thread safe, whereas some of the things that I showed you before weren't thread safe? And why is it I don't think that this is thread safe, but I know that it's thread safe? Nobody prepared to dive in and have a go? No? Okay. The reason why I know that this is thread safe are two things. First off, I know that the state within this actor can't escape it. It's within this actor and can never leave it. And I also know that only one thread will ever run within my actor at any one moment in time, because the only time that this actor will run is when it receives a message, and it will only ever process one message at a time. So I can't get this wrong. Whereas in a typical multi-threaded program, there's no way to make that guarantee, or rather, I can make that guarantee by writing a whole pile of code, and then at some point somebody might come along and call some method behind the scenes that I have no control over. This can't happen in an actor program, because the only way that you can poke an actor is to send it a message, and actors only ever process one message at a time. So this is a very simple actor. Let's take a look at a slightly more complicated one. So this is an actor called buggy cache. The clue might be in the fact that I've called it a buggy cache. If you can spot the bug, well done, but keep quiet just for a little while. It's very similar to what we've already seen. It's got some instant state within the actor. In this case, it's got a hash map called cache, and it maintains a size. And in this case, it can receive 3 messages: put, get, and report size. So we can put something into our cache, we can take something out of our cache, and we can find out how big our cache is. And then this is also this interesting little method down here, post restart, which says it's restarted. We'll come back to that. Now, in this particular actor system, I've got my main actor, the actor that actually does the work, but I've got another one, and this is one I've called master. Now, master is interesting, because what master is doing is it's a supervisor of my cache. So when I create an instance of my cache, well, in fact, I'm not going to create an instance of my cache. What I'm going to do is I'm going to create an instance of my master, and then it will go off and create the cache. So let's actually see this in action, so you see what I'm talking about. So again, I'm going to create a little console that I can play with. So I'm going to create an instance. This time I'm going to create an instance of my master. So now I've got an instance of my master. That, behind the scenes, has created an instance of my cache. So I can start sending some messages to it. And I'm going to send the messages to the master. So the master has got four messages rather: put, get, report size, and results. So let's put something in our cache. So I'm going to do master / put. I'm going to say. So we're pretending that we're caching web pages here. So I've put something in my cache, and I can check that I can actually get stuff out. There you go. It's given me the answer, welcome to Google, which is what I was hoping to see. And I can even report the size. Is it reports? Yes, report size. And it tells me that I've got 18 bytes of data in my cache, all well and good. Now, I wonder what happens if, let's say, we do something like, we have a bug, we put null into our cache. Oops, it's not get, sorry. Bang! Our cache has died. Now the reason why our cache has died, as I said, it's a buggy cache. It's not very well written. We're looking at the length of the value, and there's no check to make sure that value is non-null. So our cache has died. But notice this little message has popped up. So even though our cache has died, even though we've got a bug in our cache, we've had a null pointer exception, it's been restarted. And the reason it's been restarted is that our master has this line. So our master is supervising our cache, and it's looking to see if the cache experiences any errors. And in this particular case, it says, well, in the event that the cache has a null pointer exception, restart it. There are other things that might happen, for example. So one of the other things that our cache doesn't handle is it doesn't handle an attempt to get something out of the cache that isn't there. But our supervisor can handle that too. So if I do something like master get, so that's not in our cache, our buggy cache isn't handling that case. It's just trying to retrieve something from the cache without checking that it's actually there. So again, this is an exception that's been thrown, but again, our master is handling it. Now, it's choosing to handle it in a slightly different way in this case. It's saying, in that event, just keep on going. Even though the cache has thrown an exception, in this particular case, it's not an exception that should result in us restarting it. Now, I know this is a very quick, short example, but these techniques have been these techniques come from the Erlang world. So Erlang is a language which has been designed around actors from the ground up, and has been designed specifically in order to support very, very high availability. Chances are, whenever you make a telephone call, it's an Erlang system that's routing your call from wherever it is to wherever it needs to go. And these systems have to be incredibly reliable. There are Erlang systems that are reporting, and I swear I'm not making this up, 9 nines availability. Now, most people think 5 nines is hard to achieve. Airline systems are achieving, that's microseconds of downtime a year. And they're achieving it by using these kinds of techniques. So they're not achieving it by being perfect. They're not achieving it by writing code that never crashes. They're achieving it by writing code that can recover when things go wrong. And I don't just mean recover from errors in the code. It can also recover if the machine that this actor is running on goes down. So if you think about how to achieve really high reliability, if you want to get a situation where your code will never go down, obviously you can't put it on one machine because machines fail. I mean, every once in the hard disk will go bad, the power supply will fail, whatever it might be. If you're writing code that sits on one machine, sooner or later it will fail. The only way in which you can guarantee that your code will remain up for an indefinite period of time is to spread it across multiple machines. Now, if you do that, you're immediately dealing with concurrency and you're immediately dealing with message passing. And what actors allow you to do is to use the same approach when you're communicating within a machine and across different machines. It allows you to distribute your code across machines without having to change any of the mechanisms that you use in order to make that communication. And they add the ability to detect and then recover from errors out of the box. So, where does this leave us? I said concurrency is hard. Actually, that's not what I meant. What I meant is threads and locks are hard. Concurrency isn't hard. If we have the right tools, good tools, then concurrency can be fast, it can be scalable, it can be resilient, and a whole pile of other things. But most importantly, it can be simple and it can be correct. You have to use the right tools to get there. And threads and locks are not the right tools. So that was all I had. Thank you very much. Yes?
Aren't we losing possibility to have some kind of consistent picture with messaging sometimes? I mean, the thread and lock, I can feed everything and work on it like a transaction.
Yep.
But with message passing, that I may receive messages in different order and have inconsistent picture.
Yep, you're absolutely right. The question is, why does that matter? Now, if you care, and I think all of us care about this more and more, you care about real reliability, you have to run on multiple machines. And if you're running on multiple machines, that kind of consistency that you're talking about doesn't exist. And in fact, not only doesn't exist, cannot exist. Theoretically, it is impossible to exist because the network between the two machines might go down, you've got transmission delays. So that consistency is an illusion. It's an illusion that we've managed to fool ourselves into thinking that we've got, but in fact, we lose far more by running on a single machine and pretending like we've got that consistency than we lose by being realistic with ourselves and treating the world in the way the world really is. It's very similar to what Neil was saying in his keynote yesterday. We've been working in this world where we're using transactions. Actually, probably we're better off accepting the fact that we need to give people high availability and eventual consistency and just living with the world as the world is rather than the way we'd like to believe that it might be.
Yeah, I just wanted to mention it because you said we become simple, but actually introduces new thinking patterns.
Yes, yes. I'm certainly not suggesting that we can just work in exactly the way we're used to working on one CPU, and it'll all work that way on multiple CPUs. No, you're right. But I think it is better, and the reason why it's better is because it's a more accurate representation of the way the world actually is. I mean, you and I are concurrent, and yet we managed to talk. Yes.
I have a question about, do you see the role of transactional memory in the actor model?
So transactional memory is interesting. I think there's a very good argument for using transactional memory for some problems. I think there's a very good argument for using actors for some problems. Whether whether they play very nicely together, I don't really know. So I can certainly see a situation where you might have, for example, a system that's built with transactional memory and another system that's built with actors and some kind of high-level communication between the two. But for a low-level integration between actors and transactional memory, I'm not really sure what benefit that would give you. But, you know, never say never.
Can I follow up?
Of course.
It seems to me that the actor model is somehow assuming that your data is partitionable and that each actor can work independently on a non-shared piece of data. Actually, I don't know whether this is always the case, right? There are non-trivially partitionable, irregular applications
Yeah.
where it's really hard to split the entire data set and ensure that
So
the other side.
I think it depends.
In this context,
Yeah, it depends what kind of problem it is you're solving. If what you're after is really fine-grained parallelism, I mean, if you were doing computer graphics and you wanted, you know, you're writing a game and you want a 50 frame per second refresh rate, would I want to split my rendering of each frame across multiple machines? Probably not. That's a different kind of parallelism problem. But I think with a lot of these things, when you get into the mindset of thinking about it this way, you discover that far more problems can be broken up this way than maybe you originally think. But no, I certainly wouldn't suggest that actors are the only way to approach this. And I mean, the clue maybe is in the title of the book. I'm not suggesting that this is a one-size-fits-all thing. There are different approaches that are appropriate for different kinds of problems. But I do think actors are a particularly interesting one, yes. So there was a problem, yeah.
You mentioned that testing is very important for
Mm-hmm.
IT and the industry, and what kind of testing challenges are coming with different
Well, that's a big question. Well, so I think if I just concentrate on actors, maybe, seeing as that's what I've been talking about. The nice thing about actors is that they are an individual actor is a very easy thing to test, because once you know what messages can be sent to an actor, testing that it makes the right state changes when you send in the particular message actually is very straightforward. You don't need to worry about concurrency while you're testing that individual actor. Of course, it's not as simple as that, because you do then need to make sure that your system of actors that are all talking to each other do so in the right way. But the kinds of issues that you can hit when you do that testing are very different. You still have to worry about non-determinism, but you won't get these kinds of bizarre, I wrote this to memory and then I wrote that to memory and somehow they got reordered sorts of problems. So the set of ways in which things can go wrong is much more easy to understand. Now, I'm not suggesting that that means that it's easy, but...
That's what I meant, that if we are raising the abstraction layer of development, we're actually raising the abstraction layer of testing as well.
Yes.
Testing is more complex. It's not like easy unit testing anymore.
That's certainly true, but bear in mind that if you're writing multi-threaded threads and locks code, it's not difficult to test. It's impossible to test. It's provably impossible to test. This is not easy to test, but it is at least possible. So I think that's us for time now. So thank you, everybody. I think we've got... Thank you.